Hello everyone, welcome back. In the previous class, we derived the Lax-Volinic formula and we also verified that the solution given by the Lax-Volinic formula is a weak solution of our conservation law. So we continue a little more discussion on that function given by the Lax-Volinic formula. As I stated, there are the third part of the theorem is very much technical, so I will not handle here. And same is with uniqueness theorem. Okay, so that's also quite technical. So any weak solution satisfying the entropy inequality is unique. Okay, so we also saw examples where non-uniqueness was present. So this entropy inequality, so that's an additional condition on the weak solution. So if we impose that condition, then there is uniqueness. Okay, so another important inequality, namely entropy inequality. So now we'll discuss. Okay, so again, recall that Lax-Volinic formula. So it's given by uxt equal to f prime inverse of x minus yxt by t. So where yxt is the minimizer of the functional in the half Lax formula, and that is the connection with Hamilton-Jacobi equation. Okay, so verified this, that it is a weak solution, again using Hamilton-Jacobi equation. So you see that constant relation between the Hamilton-Jacobi equation and conservation law. Okay, now we proceed with the proof of entropy inequality. Okay, so what we have to show, again just recall. So U given by the Lax entropy, Lax-Volinic formula satisfies this inequality, or equivalently for any x1, x2, x1 less than x2, there is a constant such that U of x2 t minus U of x1 t is less than or equal to c by t x2 minus x1. Okay, so let's begin with that. Okay, so the important properties of this minimizer we already seen that. So this, for each fixed t positive, this function x going to yxt is non-decreasing, and since this g is equal to f prime inverse and f prime is also increasing, so is its functional inverse. So this there is something here. So this is not the correction there. Okay, so this, is, replace it by g of x minus yxt by t. Okay, now using that the non-decreasing nature of these functions, so we again you fix x1, x2. Okay. Consider any fix x1 x2 with x1 less than x2. Okay, so consider this expression, this g of x2 minus y of x2t by t minus g of x1 minus y of x2t by t. So just notice here this second factor is the same. Okay, so g is in particular Lipschitz uh, since f double prime is strictly positive, so you can easily check that this g is Lipschitz. Okay, so since, and then you use Lipschitz property. So g is Lipschitz continuous. Okay, so this forms. So since this is same, so the difference is just x2 minus x1 by t, and k is the Lipschitz constant. Okay, and that's related to f double prime and other things. Okay, so you can just verify that. And this also appears in the proof of Hamilton-Jacobi equation. Okay, so you can also get this result from there. Okay, now uh, this now we are using that this function x going to yxt is non-decreasing, so we rewrite again this one. So you take this negative term the other side, so g of x2 minus yx2t by t is less than or equal to g of x1 minus yx2t by t plus k by t x2 minus x1. That is the first line. And now you use that this is non-increasing, and same is with g. So this first term is less than or equal to g of x1 minus y of x1. Okay, so here we are using that. And now you take that y of x1 the other side, and you get this inequality. And this is precisely the solution by Lax-Volinic formula. This is u of x2t, and this is u of x1t, and that is less than or equal to k by t x2 minus x1. Okay, so this proves entropy. Now let's do some examples, simple examples, and see the use of Lax-Volinic formula. So these examples we have already done from a different point of view. So again, let me redo them using Lax-Volinic formula. The first one, again Burger's equation, and u of x0 is u0x. So the first example consists of rarefaction wave. Okay, so where u0x is 0 if x less than 0 and 1 if x less greater than 0. So earlier already we have solved this problem using method of characteristics. So and we got the solution as this rarefaction wave. So u of xt for t positive So 0 if x less than 0, x by t if 0 x less than t, and 1 if x is bigger than t. So this is a rarefaction wave. And let's see now this Lax-Volinic formula. So since the function defined by Lax-Volinic formula automatically satisfies the entropy condition, we should get back this rarefaction wave. And let's see that. Okay, so here f of x is equal to half x square, and so this Legendre transform. Okay, so also so easy to verify. This is also half x square, and we are interested in the minimizer. Yxt, so which minimizes this functional. So minimize y t L of x minus y t by plus w0 y. So for fixed action t, you consider this functional. So let me call by some name f of x y t. Okay, so in this case, so w0 y is integral 0 to y, so u0 j dj. So this is 0 if y is less than or equal to 0, and y if y is positive. Okay, because u0, just see here, it's 0 for x less than 0 and 1 for x positive. So very simple integral, but this w0y is not differentiable at y equal to 0, but that will not uh, create any problem in finding the minimizer. Okay, so therefore that implies f of x y t okay, so this is t into L of x minus y by t, but L of x is again half x square, so that will be x minus y square by half t square, and 1 t cancels there, so you just have the first part x minus y square by 2t plus w0. Okay, just take a look at w0, so just for illustration. So this is y, this is w0, so it is 0 here, and then 1. Okay, so at y equal to 0, it is not differentiable. In fact, it's a very good exercise. So you do need some calculus here, but you also need to analyze this. So explicitly written, so this has two parts now. So x minus y square by 2t if y less than or equal to 0 and x minus y square by 2t plus y if y is positive. So this minimizer y certainly depends on x and t. Okay, t anyhow t is positive, but x can vary over the real line, and it's a very good exercise. So I'll just uh, this minimizer y equal to so it very much depends on the position of x. So this equal to x if x is less than 0, 0 if 0 x less than t and x minus t if x is bigger than. Okay, so it's not immediately clear. Okay, there are two expressions for this uh, functional f of x y t. Okay, so you have to be careful in finding the minimum of this function. So we are interested in the minimizer, not exactly the minimum value. Okay, but minimum value uh, comes into picture in determining this minimizer. Okay, and now you just plug in the Lax-Volinic formula. Okay, so this Lax-Volinic formula, so this by the by, so just one more thing here. Okay, so f prime x is x, and so its inverse is also x, because this is what we need in the Lax-Volinic formula. Okay, so u of xt is f prime inverse of x minus y xt by t, and this is simply x minus y of xt, the minimizer. And looking at the expression of the minimizer, okay, so just plug in. So this, so if x is less than 0, it is x, so this is u will be 0. If x less than 0, and if x is between 0 and t, then it is 0, so you get x by t. And finally, if x bigger than t, then it is x minus t, so you just get 1. Okay, and this is precisely the rare fraction. So let me consider the shock wave also. That's the second example. So here again Burger's equation, only we change the initial condition. So this is 1 if x is less than 0, 0 if x bigger than 0. Okay, so everything remains same. Okay, so only now this functional f of x y t changes because this w0 changes. So now w0 of x is 0 to x u0 yt by, and that is equal to, now it is x if x is less than equal to 0 and g. Okay, and again this has is not differentiable at x equal to 0, so again it's now this, in this case w0, so we have the other, so it's just sorry, it is x. Okay, so this here and then this is the function w0, and in this case you see that again f of x y t so this it is x minus y square by 2t plus y if y is less than or equal to 0, and x minus y square by 2t if y is positive. Okay, so again for fixed x and t positive, so you find the minimizer, and here that minimum value also comes into picture. Okay, so this I'll write here, so check. So yxt is x minus t if x is less than t by 2 and x so and then you plug in just in the, so again we have, so this u of xt is equal to x minus, there is no change here because we are not changing the equation, and so this you find that it's 1 if x is less than t by 2 and 0 if x bigger than t. Okay, so this is same as again shock. So you can take some simple initial different initial functions u0 and try to work out uh, this minimization problem. In general, it's not easy. Somewhat you have to compute. So even in this simplest case, you have to really work to get these values of the minimizer. Okay, they are not straightforward. So you have to use some calculus, also some analysis of this function. Okay, how it uh, its profile for y less than or equal to 0 and y bigger than 0. Then you have to combine the analysis of these two regions separately and arrive at this minimizer. Okay, so it's, see, if this w0 were differentiable, so we could just uh, differentiate directly this f of x y t. This, if this w0 were differentiable, so the usual calculus, so you differentiate with respect to y and you equate it to 0, find the critical points and then check whether that gives a minimum or maximum, and just choose the minimum here. Okay. So with that illustration, I come to an end of this discussion on conservation law. Thank you.